Okay, so we talk about these electrochemical cells when we talk about redox reactions or electrochemical reactions. The redox reactions are going to occur in what we call electrochemical cells. And they can either be galvanic, which are also called voltaic cells, which are making electricity. They're making volts, so they're voltaic. Or they can be electrolytic cells. Now, you've seen electrolytic cells. This is a picture of an electrolytic cell. You've seen it when I decomposed the copper chloride for you. Let's have a look at what's the difference here, okay? The spontaneous ones are the galvanic cells, and we are harvesting their electrons, which you can see by putting an ammeter or a voltmeter or something in the circuit. And in a galvanic cell, you separate out into two containers the metal and a solution of its salt. So look here, here's the metal X, and here's X plus its cation in aqueous solution. And then on the other side, you've got metal Y in a solution of Y plus, okay? So like this could be copper and copper sulfate, and then zinc and zinc sulfate. So that would be what you do. And then you can harvest these electrons through the external circuit. Here's the external circuit. And then we put a salt bridge in to connect the cells to complete the circuit and to ensure that when the electrons are moving, the charge is kept constant, okay? So these happen spontaneously. The non-spontaneous kind are electrolytic cells, and you can see in here is a battery. And so when we're doing things with electricity, we use conventional current, but now we're going to look at the electron flow. So the negative terminal of the battery is going to be shunting electrons out to make this the negative terminal, okay? And then on the other side is the positive terminal. The difference here is not only here we have to put in energy, okay, this one produces energy, this one you have to put energy in, so energy out, energy in, and it's in a solution of the ions. And if you can see, both of these electrodes are actually the same metal, Z and Z, and a Z plus solution. So an electrolytic cell has got a non-spontaneous redox reaction at the electrode. So electrolytic cell is an electrochemical cell in which there is a non-spontaneous redox reaction at the electrodes. We are converting electrical energy into chemical energy. So this is electrolysis, converts electrical energy into chemical energy. And the reason it's not spontaneous is because it's got a weak reducing agent and a weak oxidizing agent. So if you looked in the table, they would have lame little values for the oxidation and reduction reactions. Okay, so it converts electrical energy to chemical energy in an electrolytic cell. You need to remember this. They like to ask you this. The reaction's endothermic. You're obviously putting in energy. We always use DC current. Remember, with AC current, the anode would be the cathode and the cathode would be the anode. It would keep flipping. So the only way to keep the anode and the cathode is to use direct current. Okay, so usually they'll pipe in an AC supply, and then they will put in what they call a rectifier to turn the AC into DC. And you need an electrolyte because you need movement of ions. So you either dissolve the ionic salt in water, or in the case like in aluminium, you actually melt the salt at incredibly high temperatures. So we need some definitions here. An electrolyte is a substance that dissolves in water to give a solution that conducts electricity. So for instance, sugar dissolves in water, but it can't conduct electricity, so therefore it's not an electrolyte. So that's the one definition. The other definition is, what is the definition of electrolysis? It is the chemical process in which electrical energy is converted to chemical energy. Or your other option is the use of electrical energy to produce a chemical change. Pick one, learn it, repeat it exactly in the exam. So, for instance, lead bromide can't dissolve. Remember, bromine salts are often not soluble, and especially not lead ones. You can melt the lead bromide, and you can use carbon electrodes, those electrodes made out of graphite like I have in the classroom, but obviously bigger. So once this is molten, the ions are separated, they can move freely, and at the anode the bromine ions will gain electrons. The bromine ions will lose electrons, form bromine gas, and let the electrons go off to the iron 2+ ions, which will gain the electrons and become lead metal, which you could use for making pipes or anything like that. And here would be your net reaction. A liquid and a liquid go to a gas and a solid. Okay, but like that really takes a lot of energy. It's much easier to dissolve stuff, and a lot of ionic salts will dissolve in water because like dissolves like. The polar water ion separates the ions out the crystal lattice. But now once you've dissolved something in water, you have to realize that the water can potentially be oxidized or reduced. So if you go and look in that table of standard electrode potentials, you can see there's two reactions. If water is at the anode, it can go to oxygen and some protons. But if it goes to the cathode, it can go to hydrogen and hydroxide ions. Okay, so obviously to decide if the water is going to react or the other ions you've got in solution, you have to look at the strength of the oxidizing and reducing agents on the table. Okay, so there's water going to oxygen or water going to hydrogen. You just have to see which one's going to happen. Okay, so this I've shown you in class, the decomposition or electrolysis of copper chloride. We've got Cl- ions and Cu2+ ions. Okay, copper is the oxidizing agent and chlorine is the reducing agent, because if you look on the tables, the chlorine ions on the right hand side of the arrows and the copper 2+ ion is on the left. So reducing agents on the right, oxidizing agents on the left. But where they are in the table, if you add their EO values together, you're not going to get a positive value. If you go EO cell equals EO cathode minus EO anode, you won't get a positive value. So it's not a spontaneous reaction. So if you put a battery in, a direct current source of electrons, you will get this to happen. You will build up copper on the one electrode and chlorine gas will bubble off at the other electrode. Now reduction occurs at the cathode. Okay, so copper is going to be copper 2+ is going to be reduced to copper at the cathode because it is gaining electrons. Okay, and reduction is gain of electrons. So this is the cathode and this is the anode. And then here's a picture here, what is actually happening. Can you see there'll be chlorine ions and hydroxide ions? Remember the hydroxide ions and the protons are from the autoelectrolysis, the autoionization of water. And when both the hydroxide ions and the chlorine ions are attracted here, but if you look at the placement of this reaction in the table and the placement of the chlorine reaction in the table, you'll see the chlorine one will be favored. And on the other side, the copper and the protons go here, but the protons don't react and the copper ions do and become copper metal. See here are the values here. Look what's happening at the anode. Okay, chlorine ions and water. This one's got a plus 1,36. This has got a plus 1,23. So this reaction occurs more readily because it's got a more positive value. So at the anode, the chlorine's going to come off because 1,36 is bigger than 1,23. And we get the chlorine off at the anode. At the cathode, there's water, okay, trying to gain electrons because reduction occurs at the cathode, but this is minus 0,83. It doesn't want to happen. And this is plus 0,34. It does want to happen. So the copper gets reduced and we get copper at the cathode. Okay, there's a table in one of your textbooks that's got substances that can be oxidized and substances that usually remain unchanged if you've got them in solution. Okay, you can copy out this table or have a good look at it and see in which situations would you actually maybe get water out and in which situations is it going to be unlikely. If you put all of these together, which one will be changed? If you put all of these together, which one will be changed? And so the water is only going to get changed if it's with a phosphate ion, a sulfate ion, a carbonate ion, or a nitrate ion. These ions are usually spectator ions. And then if you put chlorine, bromine, and iodine in, their reaction will go forward quite readily. And if you put water with sodium, aluminium, and magnesium, the sodium, aluminium, and magnesium won't be changed, but the water will. Just take this table, pause the video, and look on your table of oxidation standard reduction potentials, and look at the values of all of these and where they sit in the table. Okay, find the reduction half reaction and then check sodium, aluminium, magnesium, are they above or below this reaction? And then you'll start seeing how this pattern works. The same here, silver, copper, tin, and nickel, and water. The water won't be changed, but these will. Again, go and look on your table, look at all of these ions and see what these values are for the reactions, and then you'll see, okay, the water will be left alone if we mix water with silver, copper, tin, or nickel. Okay, so the next set of videos is going to talk about these reactions that you're supposed to know.